Hi, folks. Time to discuss number 31 in your Unit 4 homework. So what we have is this bar type of object, free to rotate about an axis through its center. Whoops. Darn it. There we go. All right. And then we have this gooey substance here moving at 20 meters per second that hits the bar and sticks to it. Now, this bar is free to rotate in a vertical plane, so later on in the problem, gravity is going to be a factor, and when we get to it, I'll talk about it. Okay, so question A, is linear momentum conserved for this problem? And think about the force interaction between the putty and the bar, but also think about the other contact point acting on the bar, which is here at the pin. So that will hopefully tell you something about A, whether linear momentum is conserved or not. Okay. B, is the angular momentum conserved? Well, ask yourself, is there any net torque acting on the system during the impact? Particularly, you want to sum torques about the axis of rotation. Part C, find the angular velocity of the rod just after the impact. Well, you're going to end up using angular momentum to solve this, all right? So the picture of the system right before impact, the putty, this object has an angular momentum about that central axis equal to its linear momentum, mv, times this distance, L over 2. Okay, now imagine the putty is stuck to the bar and the entire thing is rotating. You can express the angular momentum now as an I2 omega 2, where I'm just putting the 2's in to denote after the impact. The I2 is going to have two terms to it. You've got the bar, and I'll go ahead and tell you, it's 1/12 ml squared for the bar. But you also have to include the putty, so you have to add a m times this distance squared for the fact that the putty is part of the system. And then you can calculate an omega 2 out of that. It should be no problem at all. Part D, find the maximum angle. Ooh, 8, that's supposed to be angle. I'll have to change that. Find the maximum angle reached by the 1 kilogram mass after impact. So here's a picture of the system, free to rotate. Here's the putty stuck to it, and it's rotating this way with a speed, let's say omega 2, that hopefully you found. What you want to do now is assume it rotates up to some angle. Now I'm going to draw the angle something like this. Here's our putty. Here's theta, the angle. Now, write a work energy theorem between picture 2 and picture 3. And I would put the datum through the pin. And I'll help you out with this a little bit. The bar is not changing in potential energy at all, so you don't need to worry about the bar. The potential energy in position 2 for the putty is minus mgl. Now, picture 3. The putty is this distance below the datum. That's your h. And that distance is adjacent to the angle theta. So your PE3 term should look like minus mgl over 2 cosine theta. I want to go back and talk about position 2 again because I might have accidentally said minus mgl. If I did, I meant minus mg L over 2. This distance right here is not L. It would be half of L, 1.5 meters. Okay. And going back to position 3, this distance is L over 2 cosine theta. Right, so your PE3 term is going to look like a minus mg L over 2 cosine theta. So get that written out in the work energy theorem. Now, I suspect some weirdness might happen with this problem. I made these up completely off the top of my head. I shouldn't say weird, but I'll say this. There is some mathematical interpretation that you may need to consider. After you write the work energy theorem out and you simplify this, you should be able to get it all the way down to cosine theta equals some number. Now, here's where a little more trigonometry comes in, all right? If that number is between 0 and 1, you will get an angle out between 0 and 90 degrees for theta, somewhere in that region. Problem done. No problem at all. If this number ends up being between 0 and minus 1, that's no problem at all. What will happen is when you take the inverse cosine, you will get an angle between 90 and 180. And that's physically possible. You know, just imagine this object doesn't end up here. It ends up here somewhere. That's going to give you an angle like, 130 or something like that. And again, you're going to be done. No problem. But the other possibility that might happen is this number might be bigger than 1. It might be like 1.5 or negative 1.5 or something like that. If you get a number like negative 1.5, that means this equation has no solution to it. And I'll let you think about physically what would that mean. It does not mean there's a mistake in the way the problem is written. There's kind of a physical interpretation of that. And I'll let you think about that and we'll discuss it in class. So anyway, I hope that this helps. Have a great day.